Thanks for the introduction. So indeed, I'm from the Grove of Valerius Garani. I'm a PhD student there. And so the first half of what I'll be talking about today is about quantumness. And this was just recently published like a month ago. And the second half is about detecting entanglement. And this is so fresh off the press that when we announced this talk, it wasn't even out on the archive. So there's brand new stuff, which I'm glad to be sharing with you today. So to start off, I just want to start with the motivation for why we even started working on this. And it's actually this simple question. What is quantum about a quantum harmonic oscillator? And you know, I had a chance to give this talk to a bunch of undergrads, and this is the kind of answers you get. Like, you have discrete energy levels, or if you cool it down, you can't cool it down below half h bar omega. Or it's because of you can't measure the position and momentum precisely at the same time. But these are negative properties of a quantum system, right? These are what quantum systems cannot do. So if you're at a box with a harmonic oscillator, and you find that you can't measure position and momentum precisely, it doesn't mean that you have a quantum system. I mean, it doesn't have to mean that you have a quantum system. It could be that your measurement devices are not good enough. So in some sense, classical systems can kind of fool you into thinking that they're quantum systems if these are the only properties that you look at. So what's the for sure way to detect whether or not something is quantum? Of course, you can't beat Bell inequalities if you have two harmonic oscillators far apart. Or if, under some assumptions, you can do some kind of non-contextual inequalities, right? Or if the system is small enough and you can fully tomograph the system, and you find that the state is some kind of non-classical state, then you're sure that your system is quantum, right? So for these behaviors, if you detect these behaviors, it has to be quantum for sure. And so this is the kind of property that we want to find. And actually, the converse question is also kind of interesting, right? Which is, what is not quantum about the quantum harmonic oscillator? And it's actually its time evolution, right? If you have a classical harmonic oscillator, and the initial state is somewhere there, its evolution in time is just a precession around phase space. And if you have a quantum harmonic oscillator, you can have the fanciest state you want with all the negativities in the middle. But the time evolution is still just a precession around phase space. So the time evolution of a quantum harmonic oscillator is as classical as it gets, right? You don't expect to find anything quantum by looking at the dynamics of a harmonic oscillator, unless you're Boris Tsirelson, right? And so, so from his Darcy archives, there's this procedure, right? How often is the coordinate of a harmonic oscillator positive? So let me kind of go through this procedure. And I like to think of it as a game. I understand it more as a game. OK, so the assumption is that you have a system which is a harmonic oscillator with a period t that you know. So in this game, you play many rounds. And in each round, you prepare the system in some state. You wait for a random duration, 0, 1/3 of the period, or 2/3 of the period. So just as an example, I'll roll a 3-sided dice. And let's say I get 1/3 of the period. So what I'll do is I'll wait 1/3 of the period. I let the system evolve. And then I go on to step 3. I measure the position of the system. And all I want to know is whether or not it is positive. So in this case, you can see that it is positive. So I do this many times. And after many rounds, I calculate the score, which is how likely is the position positive over these many rounds. And a comment I make here before I go on, which is that we are doing independent rounds, right? In each round, we reset the system, or we can perform each round on an ensemble of identical oscillators. We're not doing any kind of sequential measurements here. OK, so keeping that in mind, let's kind of do a test run of this protocol. So I have an initial state like this, right? I roll a dice. I get t equals to 0. So I measure the system immediately, and it's positive. So I roll the dice again. This time I get 1/3 of the period. So I let it evolve a little. I measure the position, and this time it's positive. So I roll the dice again. This time I get 2/3 of the period. OK? And I let it evolve slightly longer. I measure the system, and this time the position is negative. And so I repeat this many rounds. And each round, I prepare the system in some state. I roll the dice. I wait that amount of time. And I measure the system. And after many rounds, in this case 12 rounds, I find that it is positive 8 out of the 12 times. So my score here is just 8 over 12, or 2/3, right? So it should be clear that if we repeat this many rounds, 1,000 rounds or so, then really the score is just the average of whether it is positive at time 0, at time 1/3 of the period, and time 2/3 of the period. And so let's try to see in the classical case what kind of score we can get. Right? So in this case, we already see that the score is 2/3. And if we repeat this argument for every single point in this orange region here, we'll find that the score is always 2/3. Right? And if you're somewhere outside the orange region, and I let it evolve to 3 different times, and measure the position, this time it's only positive once out of the 3 times. And so for every point in the blue region, the score here will be 1/3. And so this is all the possible classical scores that you can get. So the most general classical state, which will be some kind of probability distribution over x and p, of course, you can only obtain somewhere between 1/3 and 2/3 for the score. So 2/3 is the best score that you can get in the classical, for the classical harmonic oscillator. So we'll call that the classical bound, 2/3 the classical bound. And if you're given some initial state like this, and you really wanted to calculate what the score you'll get, then all you need to do is define 2 integration regions, one over the orange region, which I'll call I+, and one over the blue region, which I'll call I-. And the score for this is just 2/3 of I+ and 1/3 of I-. So this is the classical case, right? We know the best you can do is 2/3. The best score you can get is 2/3. So what about the quantum case? I like to reason the quantum case, at least for the harmonic oscillator, in terms of the Wigner function, because a lot of the arguments we had before kind of carries over just by replacing the joint probability density with the Wigner function. And this is really because the action of measuring whether the particle is a positive x plane is just the integral of the Wigner function over the positive x plane. So and the time evolution is again a precession in phase space. So I can track every single point of the Wigner function, and I can repeat the exact same argument I did before. So following the same arguments, I again define the 2 integration regions, I+ and I- over the two regions. And again, the score is just 2/3 of I+ plus 1/3 of I-. So everything here is exactly the same, except that I replace all my density, probability densities with the Wigner functions. So what's the difference between the two? Well, the difference is that the Wigner function is not really a probability distribution. So we all know that the negative Wigner function is kind of the most non-classical thing you can get, and this is the same here. We can allow negative values in the Wigner function as long as the marginals are still probabilities. So what if we take all the negativity and we concentrate it on the I- region, right? What happens is that because of normalization, where it has to add up all to 1, the positive regions will become even more positive, become even larger than 1. And so the score here, if you notice, this becomes even larger than 1, and this adds up. This score can add up to something that's larger than 2/3, larger than the classical bound. And indeed, this is what we find. If we kind of optimize for the largest quantum violation under some energy truncation, the state looks like that, and the score you obtain is something like 0.709, which is clearly strictly larger than the classical bound. So quantum harmonic oscillators can be the classical bound. One thing to note, because I often get questions about this is the optimal state, but you don't need something so complicated to actually beat the classical bound. So the simplest case I can think of is something like a superposition between 3 number states, 0, 3, and 6. Or alternatively, you can have a 3-headed cat state. That also beats the classical bound. And the symmetry is not really necessary, but it's easier to kind of work out if you have that symmetry also. Yeah. So this is the case for beating the classical bound. And everything I've told you about can be found in Tsirelson's original paper, right? Except for the nice graphics, but everything else you can find in Tsirelson's original paper. So what did we actually do in the paper that we recently published? Well, we looked at some generalizations, and of course the most obvious one is, what if we probe the system at k different times instead of just at 3 different times? And well, for k odd, we can do the exact same kind of arguments for any k odd, where we can find some classical upper bound, right? Where we can find the maximum classical score. And at the same time, we can use the same kind of arguments and put the negativities in the negative regions, and we find states that can violate the classical bound. And so the question is, can we actually always find a quantum classical gap for the different values of k? And how large, how much can we actually violate the classical bound? And in other words, what is the lowest bound of the maximum quantum score? And what is the upper bound for the maximum quantum score? And is there always a gap? Yes, for finite odd k. And we know this because we have a closed form lower bound for the maximum quantum score that is strictly larger than the classical bound. And so we know for sure that for any value of k that you give me, any finite value of k that you give me that is odd, I can beat the classical bound. It doesn't work for even for symmetry reasons. For even, it's the same for both the classical and quantum case. Well, this is the form for it. It's not that important, but I put it here for completeness. How large can the quantum classical gap be? So what is it? It's defined in terms of some a cosine, sum of a cos inverse, yeah. Yeah. So so how large can the gap actually be? We know that it's a probability, so it cannot be more than 1. Tsirelson's paper showed that it is strictly less than 1, but it can be epsilon close to 1. And in our paper, where Werner was attending a similar talk given by Valerio and casually mentioned that he did something similar in the late 80s, we managed to improve this bound to a constant larger than the classical bound, where the constant is something like 0.1559. So basically, you cannot do arbitrarily better than the classical bound. You can only go up to a certain constant larger than classical bound. But even this bound is loose. And we know this because we know that as k goes to infinity, both the classical and quantum cases will converge to half. And so even this, which is improved from the Tsirelson's paper, it is still quite loose. And this is, it's forever in our minds since we started this project. OK, so that's for the obvious kind of generalization. The other generalization we looked at was, it doesn't have to be a precession in phase space, right? You can have something that's actually precessing in real space. And this comes about because if you have a Hamiltonian that is just the angular momentum Jz, then every vector that you have precesses in this way, right? Where the x and y components precesses uniformly. And so would this protocol also work where we just replace measuring the x with measuring the x component of the vector? And well, if you repeat the same kind of arguments, you'll find that there's no change in the classical bound because you don't really care in the classical case what the actual variables are that are precessing. So the same derivation will give you the same classical bound. But you'll also realize that if you want any kind of violation, it wouldn't work with if Vx and Vy are compatible, if they commute. Because if they commute, you can find some joint probability distribution. And so it wouldn't beat the classical bound in that case. So for that reason, you can't use actual position x and y to precess, to find some classical violation of the classical bound. But maybe it might work for gx and jy, for the angular momentum, because gx and jy do not commute. And that was what we looked at next. How often is jx of a uniformly precessing system positive? Right? So we can consider a fixed value of j. Well, because every angular momentum system, you can write it as a direct sum. So it's sufficient to just look at each value of j at once. And each value of j gives you a finite Hilbert space. And so if you have some initial state, then the score, the quantum score, is actually just some expectation value of a POVM. Not POVM, sorry, observable. And you can write this observable like this. So these are just the time evolution operators that evolve the k different times. And this is just an average over them. And so pos jx here is defined in this way. And if you check, you put a ket of any eigenstate of gx, you'll get 1 if it is positive and 0 if it is negative. So this is the operator that where you take the expectation value, it gives you the quantum score. So if I want to find the maximum quantum score, actually it's just the largest. So 0 is half. And there is a long argument to be made, which I will gloss over, and we can discuss this later if you are interested. Yeah. So basically, 0 is there's a singular it's a singular behavior even in the quantum harmonic oscillator case. Yeah. So half is the one that makes the most sense for the weight. Yeah. So anyway, the score here is just the largest eigenvalue of this particular operator. And this time, d is finite. So we can solve this exactly. And this is what we did. And this is what we find. So here, for different values of j, x is the different values of j. And on the y-axis is the maximum quantum score. And there are a few features. One, which is that the first few values are always half. And then it jumps all the way up to something very large. And it comes down again. And there's this kind of weird oscillatory pattern here. So this gray line is the maximum classical score. And all the way on the right, in red is the lower bound of the classical. Yes?
You can finish your sentence.
OK. in red is the lower bound of the quantum harmonic oscillator case, while in blue, we calculated this to like j equals to 2,000 or 5,000, something like that, and we averaged it out to get some sense of what the asymptotic behavior will be. Yeah.
I wonder if there's a way to understand, or if you understand why the first cases of j are at 1/2, and then they jump.
OK. So I'll show you k equals to 7, and then we'll talk about that. OK. So k equals to 7. Very interesting. Got the same thing, right? And then it jumps up, and it does that. And again, this is the classical bound, and those are the asymptotic values and the lower bound in the quantum harmonic oscillator case. So maybe to kind of put attention to the significance of what's happening on the right, what we are seeing is that it seems that asymptotically, we are approaching the quantum harmonic oscillator scores, right? So that's kind of why we put that there. So to address your question, indeed, we find that the maximum quantum score is half as long as the dimension is less than or equals to k. And this is because if your dimension is less than or equals to k, it happens that this averaging results in a unitary T design. And so unitary T design. So essentially, so unitary T designs are like if you want to average over a circle or a sphere, right? And you want to integrate over the sphere. The question is if you have, let's say, at most power of 1 or power of 2 function, instead of doing an integral, you want to take finite sample points to calculate that average. So there are different ways, there are different T designs, like 2 design is like power of 2, 1 design is power of 1. But the general idea is that if the dimension is small, then given the dimension, there is a certain number of points you have to sample, right? And so it happens that if your dimension is less than or equals to k, k is the number of points you are sampling in some sense. It happens to give you the average of over the sphere, or in this case, over the circle. So, and
if I were to reverse the problem, is that if I sample for a given dimension, if I have enough
Yes, exactly. And of course, if you average over the sphere, all you get is whatever's at the center, right? And yeah. So that's kind of what's happening. So if you average over, you find that you get half identity. Yeah. So that's why we have this behavior at the start. Yeah. So the other thing I mentioned was that it seemed to approach the quantum harmonic oscillator case, even though we don't actually know what the actual, let's say the proper maximum for the maximum score for the quantum harmonic oscillator case is. We know that it has to approach that, whatever that is. And we know that because somehow the operator QK approaches the case for the, the matrix elements of QK approaches exactly the matrix elements of the quantum harmonic oscillator case. So we know that asymptotically they should agree, even though we don't actually know what this value is. Yes?
Have you looked at other eigenvalues of this matrix?
Other eigenvalues?
Other eigenvalues, maybe like the smallest one, or like what behavior do they have? Are they also periodic?
Okay, we have some idea of what the other ones are. So for example, from the symmetry, we know that the smallest one has to be something like related to the largest one in a certain way. But we have not, let's say, plotted every single eigenvalue. Yeah, it's only the maximum and from the symmetry, the minimum that we have looked at. Yeah. Yeah. So this is the asymptotic behavior. We notice a peak always at the dimension where right after you get the trivial behavior. We always find a peak there. We don't know why this happens. We know there's a peak there for all the points that we know analytically, which are the red dots. Those are the only points we actually know analytically. But for all the ones we know analytically, that is the largest one. So this is still kind of, we don't really understand. And it repeats every 2k points. And this is a similar situation where we know, for the points that we know, it has this behavior. We don't really know, in general, why this is the case. Yeah. So this is kind of a sketch of what we've done with the angular momentum. And I think yes?
You know what, there's always 3 that also triples that form. You know what those are?
I know the expressions are the same. I couldn't like give you a physical sense of why that seems to be the case. Yeah. Yeah.
They're the same. Those triples really give you the same one.
Yeah. So at least for the analytical ones, those 3 plateaus are exactly the same. Yeah. Okay. Okay. So yeah. So for k equals to 3, you realize that every 6 points, the pattern is the same, but squash. Yeah. I mean, one of the ways we were trying to bound this was to try to find the envelope of this graph, but that really went nowhere. Yeah. Okay. So yeah, this is the angular momentum case. And so for everything that I've described, really, the idea is that we have this kind of protocol to certify quantumness by using precessions in harmonic systems, right? So yes?
Just maybe a general question, but like when you say that you're certifying quantumness, aren't you rather like also maybe even going back to the harmonic oscillator, aren't you rather just certifying that you do not have a classical harmonic oscillator?
Yes.
It's like coming back to maybe your very first slide where you said maybe my classical system is kind of lying to me, or my device, so you could have another classical system that is not a harmonic oscillator, and I guess gives you the same bounds. So in a sense, could one argue that this is not, like certifying quantumness, it's more certifying that it's not a particular classical system?
Yes. So it's certifying quantumness under the assumption that you know, okay, so how to put it? You know that it's a X system, a particular system. You just don't know if it's the quantum version of that system or the classical version of that system. Yeah. So it is certifying quantumness given the assumption that it is indeed a harmonic system. Yeah. Yeah. So yeah, it's not super general in that sense. We still have to kind of assume that we know the dynamics exactly. Yeah, yeah. So, yeah, indeed. So, I mean, it's going to make a much longer title if I kind of put all the nuances. But the idea is there. Like, we want to kind of certify quantumness with precessions in harmonic systems under the very important assumption, as you rightly mentioned, that we know that the dynamics of the system is a uniform precession, and that we know the period of the system, right? So only if these assumptions are true will this protocol work. And this protocol is really just performing many rounds, where in each round, I prepare the system, I randomly wait some duration, and I measure whether x or jx at that time. And after many rounds, I calculate the score, which is how likely is the thing I measured positive. And if I find that it beats the classical bound, then this precessing system is quantum. And let me finish this too. Quantum classical gap is what allows us to certify non-classicality without the need for this kind of sequential or simultaneous measurements that you might need with non-contextual inequalities. Did you have a question?
Yes, I do. So when I read your paper first, I was under the impression that you need to assume purity. I mean, for your Wigner function to have negativities, or like to say that it cannot be a classical probability distribution. I mean, a quantitative probability distribution. Now I realize maybe you don't need this, and indeed you don't put it in your assumptions. But do you have results already about what happens if your state is mixed?
The only condition you need is negativities in the Wigner function in the correct places, in some sense. So yeah, indeed, you can easily mix, have mixed states that violate the bound. Yeah.
And then how bad would it be if the dynamic is it's a harmonic oscillator, but it's lossy, or it's
lossy?
Yeah, well, it's not a unitary.
Okay, lossy.
Okay, it's not a unitary. Sorry.
Okay. Okay. We have not really looked at that yet. Yeah, but I mean, obviously, at some point we will. Yeah. Yeah. There was someone else.
Yeah. So you also need to prepare always the same initial state.
So in the asymptotic limit, right, where you perform 1,000,000 different rounds, it doesn't really matter, right? Because even if you prepare slightly different states each time, it just, in the end, you just get some rule, like some mixed state. So indeed, if you have if you do only a finite number of rounds, you have to do some kind of statistics to say, okay, like, is this actually correct or not? But for now, we're just looking at, let's say you really do an infinite number of rounds, right? Yeah. Okay. Yeah. So this is actually a good place to move on to the next topic. And just as a bridge, actually, in the protocol we discussed, right, we are looking at some kind of precession. And we already saw that we started with harmonic oscillators precessing x and p, and then we realized that we could do it with gx and jy. But actually, it doesn't necessarily have to be a gx and jy of a single system, right? You could have some kind of effective oscillator, because if you have two precessing variables and you add them up, right, it's still uniformly precessing. So for example, if I look at a system which has two different spins, but with the same frequency along jz, then you can perform this protocol with the total angular momentum. And actually, what you find in that case is that if you have the total angular momentum and you maximally violate this protocol, you will find that it's always entangled. So somehow, just for free, just by looking at composite systems, you get some kind of entanglement witness. And for a very particular case, if you have k spin half particles and you have the maximum violation, it self-tests the GHZ state. And you saw just now that the peak was actually, quite a lot larger than the next peak. And so it's also kind of robust, although we have not really, let's say, really calculated how robust and things like that. So kind of just for free, we get these things by looking at composite precessions of composite systems. So naturally, we want to ask, okay, if that's the case for angular momentum, what if you have two harmonic oscillators? And in this case, they can be coupled, they can be not, but we can always write it in terms of its normal modes, right? So if we have this kind of harmonic oscillator, and we perform the protocol on one of the normal modes, right? X plus or X minus, just on one of them. If we violate the classical bound, can we say anything about the entanglement? And that is kind of the natural the natural next question that we have. And so ideally, what we want is we want to witness entanglement with uniform precessions, where we assume this time that we have two harmonic oscillators, and we know exactly what its dynamics are, right? We know exactly that it's in this form. And the period of the normal modes, we also know, okay? And again, the protocol is very simple. For each round, prepare some state. We randomly weight a duration. I'll just stick to the simple case, except now we weight 0, 1/3 of the normal mode period, or 2/3 of the normal mode period. I measure x1 and x2, because x1 and x2 are usually what you actually have physically, right? And at the end of the day, after many rounds, you calculate the score, which is how likely is the normal mode positive. And we already know that if you have a classical state, you cannot beat the classical bound, right? If you have Gaussian states, for example, you cannot beat the classical bound. But what about the score for separable states? That's kind of interesting. So let's say I will look at this very particular special case where the normal mode can be written in this way. I'll come back to what this case actually is. But let's say we have this case, right, where the normal mode can be given exactly as x1 plus x2 with the weights proportional to square root of their masses. So we take a separable state and its corresponding Wigner function. So let's say a state is of this form. The Wigner function has to be a convex sum of the product of the two Wigner functions. Now, if I'm performing this protocol on only one of the normal modes, let's say x plus, then we don't need the full Wigner function, right? We only need the Wigner function in the x plus basis in order to find out what the expectation value, the score will be. So if we take the reduced Wigner function in the x plus basis, I'll get something like this. For some unitary, so this u here is just some unitary that is dependent on the x plus and p plus in the arguments of the Wigner function. And rho 1 and rho 2 are exactly a rho 1 and rho 2 there. So what you realize actually is that this is just a convex sum of the inner product of two density operators. And so this has to be positive, non-negative. And so because it's non-negative, I can always find some classical, a state in a classical harmonic oscillator that has this exact same probability distribution. So it cannot violate the classical bound. So in other words, if my rho is separable in this special case, then I cannot beat the classical bound. Or conversely, if I beat the classical bound, I know for sure that rho is not separable. And in other words, if I beat the classical bound, the two harmonic oscillators that I have are entangled. And this kind of completes this protocol for the special case where the normal mode is given in the form I mentioned before. Just a test run of some notation. Valerio suggests that we call this a dynamic-based entanglement witness. I would accept any feedback on this particular term. It's not even in our archive because we want to run through it before we actually submit and yeah. So yeah. So I'm showing you the nice part first, which is the parts which we actually have analytical results. But in general, if you have a coupled harmonic oscillator, more generally, the normal mode will be of this form, right? Where it is some cosine theta and sine theta, where the theta is given by, fixed by the system parameters. And so if you look at the annihilation operators of the two modes, then theta are exactly the kind of beam splitting angles that you need to turn it into the normal mode. So if I have uncoupled oscillators with the same frequency, then actually theta can take on any value. And of course, it's best to choose theta, which corresponds to the previous case where we have analytical results. So the analytical results basically corresponds to a case where it's exactly a 50-50 beam splitter, or when theta is pi over 4. and we had to use numerical results for other values of theta, which I'll kind of present now. So for the numerical results, we studied the protocol for k equals to 3 using the log negativity, which I think I've spelled wrongly. Yeah, log negativity. And we studied this by performing this SDP program, where we minimize the log negativity subject to the score being a certain amount. So in other words, if I observe a certain score, what is the lower bound on the entanglement that I have, given that I observe that score, right? So this is kind of the plot that we see. And the color here is the log negativity. And the y-axis is the score, where right on top, that's the maximum quantum score that you can have. And on the x-axis is the mixing angle theta. So, yeah. There's a truncation, and again, argument for truncation where we truncated at different values, and then we kind of find what was the lowest entanglement we had for that truncation. And we chose that truncation because it kind of gives us a conservative estimate for what the lower bound would be. Yeah. Yeah. So this is kind of the results for that. And I mean, what we clearly see is that it increases along that direction, right? So the entanglement increases with a larger violation and with a larger mixing angle. But the thing here is that if you're away from the best case scenario, then you might need larger violations to witness some kind of entanglement. So everything on the right side of this particular dashed line, up to the gap, we know for sure that it is not 0. So everything on the left might be 0, might not be. So yes.
Sorry, can you repeat what it means? S-sample coming to be within this dashed line?
Mm-hmm. So
I had understood that P3 larger than 2/3 is a witness of entanglement.
Yes, P3 is a witness for entanglement if the mixing angle is pi/4. Yes, for sure. Yeah. So that's the one that we have an analytic. So it's this particular line we have an analytical result for. Everything else is numerical. Yeah. Yeah. And so the dashed line here separates no entanglement from having entanglement. And yeah, so if you are beyond this, somehow you need a larger entanglement, larger violation to detect some kind of entanglement. And of course, if theta equals to 0, actually this is just you performing the protocol on one of the oscillators. And so of course, no matter how much violation that you get, you can't detect any kind of entanglement. Yeah, so this is kind of how the graph is read.
Actually, can you say something about the color code, because we cannot see it here?
Yes. So the largest value is, sure. No, I think there's something behind. Yeah. It's okay. Wait, I will do this. Yeah. 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 So I mean, this is the kind of the lower bound for the entanglement for the given violation. Yeah. Okay.
We agree that this is a sufficient criteria.
Sorry?
It's a sufficient. You're not detecting Gaussian to most states, right?
No.
And there is no way around this.
No. If there is some way to classically simulate your state, then there's no way that anything I talked about today will work. Yeah. So this is kind of backwards because usually you start with the motivation, but maybe going back to the motivation. Why were we actually looking for this? Well, it's because commonly used criteria, right, for continuous variable entanglement is based on quantum uncertainty relations. So, I mean, the common example is Duan et al., where if you have some real number, you can define this kind of EPR-like states, sorry, EPR-like variables, where x tilde and p tilde are the dimensionless versions of x and p. And you'll find that, okay, if you have the variances lower than some threshold, then it's entangled. Of course, like this requires you to a measurement precision that is set by h bar. And also, if you realize if you have sufficiently pure classical states, then this left-hand side kind of goes to 0, right? If you have sufficiently pure classical states. And so somehow, if you have a harmonic oscillator, two harmonic oscillators that is classical, which for some reason the Heisenberg cut actually exists and it's classical, then you will be open to false positive, right? It will falsely kind of tell you that these two systems are entangled when in fact they are just classical. So this is kind of the motivation for why like my group was interested in this, and these issues really become more important as you start to entangle more and more massive objects, which which some of you are doing in Vienna here, and yeah, this is kind of the motivation for why we started looking at this. And I'm not saying, okay, probably what we have published or what's up on the archive will not really be used the way it is, because we're not saying that our criteria is better than everyone else's, right? There might be a reason why you might want to use ours, and there might be a reason why you might want to use other criterion. So to make it simple, like this is the comparison. So this is the motivation, which is we don't have false positives if you have a classical system. But conversely, as was mentioned a few times, we cannot detect any Gaussian entangled states. So the usual entangled states that are kind of more straightforward to prepare is not going to be detected by our criteria. This is an annoying one. So in theory, our DEW, again, practicing the terminology, our dynamic-based entanglement witness, is supposed to detect some kind of bound entangled states. And you can prove this by showing that it's a non-decomposable witness and blah, blah, blah. But we have not managed to find any. So in theory, we should be able to find one. Just haven't found any. And for a very specific example of a family of states, we constructed this peculiar family of states. And we could show that actually none of these criteria can detect these states, while ours can. I'm not saying anyone should prepare this, but this is just to say that, our criteria cannot detect Gaussian entangled states. And so, there might be a worry that it's a subfamily of these bigger families, but this kind of shows that it's just not the same family. Yeah. Yes.
Do you have, is there a hint that maybe the only entangled state that you cannot detect are the Gaussian ones? Chance that this is this, or actually?
I would say it's quite unlikely because it's kind of like where do you cut this set, right? And so it's very unlikely that you can cut exactly so that it cuts around the Gaussian states. Because all entanglement witnesses are just like this kind of hyperplanes.
So actually, I think I can formulate the question of whether pure entangled states, except for the Gaussian ones, have negative function.
No. So if you have negative Wigner functions, but let's say all of them are clustered in the origin, our criteria cannot detect it. Yeah. So that is an interesting question I've been trying to think about, which is, let's say I have my criterion, and I'm allowed to do some Gaussian operations on it, which preserves the negativity. Can I still kind of detect every single negative state? I'm not sure what the answer is. Yeah. But as it is, if you have some kind of symmetry, then you cannot detect it either. Yeah. Yeah. So the last point is really just to show that it's a different. Our criterion and these criteria are different families of witnesses. So yeah, this is really all the work that we have done in the 2 papers. Just a quick overview of what we are currently looking at. Indeed, it might not be that you have exactly a harmonic system, right? This is a very ideal kind of system, and so we're looking at general bound systems where we extend this to n-harmonic systems, where we have to add in some additional assumptions. And just visually, I'll show you what these assumptions are. So if you have this kind of n-harmonic system where the period depends on the energy, then you can put some kind of energy bound on it, where everything within the energy bound has a probability of, let's say, the maximum classical score of 2/3. And so you can simply use this criteria again, and you get the similar Wigner function, but with like slightly more distorted. This is what I should be working on. We are writing the manuscript now, and I should be doing this now, but I'm procrastinating by being here in Vienna. So that's for general bound states. But why I'm actually here in Vienna is to kind of learn a bit from Miriam, which is to look at some general theories, more general theories. And so we want to compare the predictions in quantum theory versus what some GPTs predict. And it's a pity that, what's his name? Lorenzo, who was here last week, gave a talk about his epi-restricted models and stuff. This is our protocol is one example of where epi-restricted theories are not enough to explain this behavior. We actually show, well, in the conclusion, we kind of mention how all of their epi-restricted states cannot go even beyond the classical bound. So yeah, so that's kind of the outlook for our work. And conclusion, if you want to detect quantumness, given that we know the dynamics and it's a harmonic system, we just ask how often is the coordinate positive. And to witness entanglement, we perform the protocol just on the normal mode of 2 oscillators. And I thank you for your attention. This is our group. Interestingly, 2/3 of our group worked on this project. And special thanks to Miguel for so I'll end with the anecdote since, okay, I won't end with the anecdote. You can ask me the anecdote later. But thanks to Miguel for bringing Tsirelson's paper to Valerio's attention, who brought it to our attention. Yeah, thank you very much.
It's just a discussion feature.
Ah,
so
okay.
questions?
I would have a question.
Yes.
Because I remember also, like, at least the first part of this talk from this Tsirelson workshop, and it was also mentioned that the analytical formulas are just too complicated to derive anything like this asymptotic behavior and so on. Do you have by any chance somewhere like these formulas written? I'm just curious how complicated they are, like if you have them somewhere.
So which part?
This oscillator behavior
Yes.
in the first part of your talk, and you mentioned that like the formulas are super complicated, and that's why analytically you just calculated the first couple of
Yes.
values. I'm just curious if you have somewhere that the formulas themselves.
Yes, in my appendix, which is about 5 times longer than the actual paper, you can find the, yeah. I mean, even for the points that we know, it required many special cases and many recursions to even work out, yeah. Yes.
So I think that the open dynamics would be very interesting. Also, it would make in my experience, having a harmonic oscillator it's a very good assumption even in experiments as soon as you have some sort of losses or open system. So it would kind of remove the fear that maybe nature is conspiring against you. And yeah. So I wonder, is it on the agenda or not? I mean, I guess that all the numerics kind of stops at 50.
Yeah. So not right now, mainly because let's say we don't really have expertise in these things in our group. But of course, like, because it's a natural question to ask, maybe I might end up working on this in like 6 months or something. Yeah.
But would your question be like you take some like Lindblad equations instead of just
or quantum dimensional equations? I think, I mean, experimentally, as far as I know, moving too much in some sort of potential in the presence of a strong bar, then the harmonic behavior will, or especially the Gaussianity will come out.
Okay, okay.
Maybe one more.
Yep.
Did you, like, also from this experimental perspective, did you consider the uncertainty with which you can measure time? Because, like, again, like the first part of the talk was like either after t-thirds or two-thirds of t.
Right, right.
How does this affect your results? Do you know?
No, I don't have an answer for that, yeah. I do have a similar thing I'm looking at, which is with the anharmonic systems, because in that case, we don't have a particular period, right? And so indeed, there is some kind of dependence, some kind of peak exactly when t is the period, but it kind of dies down at the side, yeah. Yeah.
Is there like general statements about like going beyond even, you know, like the two cases basically you talked about, like that anything that is periodic there, I will always be able to construct, I don't know, like you know, like measurement times at which I should measure such that there will be a gap. Like, is this? Do you reckon that this can be generalized to? I mean, maybe just very theoretical. Like, there will always be a bound. Like, quantum systems are always like of periodic dynamics will always outperform. Or I can always find a scheme for which I outperform the classical case or something like that.
I've actually only begun looking at this in a week or two, but so far what I know is, so the half, right, the trivial behavior at the start, I know that is true for any precessing variable. So in the quantum case, you have a lower bound on the dimension you need in order to get these behaviors. And yeah, we have some other things about, let's say, the score you can get if you can actually get something larger than the score that we saw here, but under some like artificial constructions and things like that. So yeah.
So about kind of the weakness part, like you have these two harmonic oscillator and this coupling, or family of couplings. Do you think that this result that you can certify entanglement that way, is this specific to this coupling, or do you think this is kind of a general thing that if you have interacting systems, you can expect to do similar things?
I mean, we expect what we saw on the graph, which was that with a lower kind of mixing, you need a larger bound to witness entanglement. We have not been able to do anything more analytically than what we have so far. Yeah.
One more, sorry.
Yep.
Actually, again, drawing back to this connection between K, this capital K, and the dimension of the system, can you actually use it to derive some dimensionality witnesses?
Yes, it's what I mentioned. So, yeah. And this was literally, I just worked this out last week, so nice.